Okay, so modeling with exponential and logs. Okay, so first thing is just to kind of help you understand, there's this exponential growth or exponential formula here. Okay, and it looks like this. So y is equal to a times 1 plus or minus r raised to the t. So there's a couple of things that we want to understand about this equation here. This is the final amount, whatever that final amount is. And the problem will always tell us that information. A is going to be the initial amount, starting amount. And R is the rate, the growth or decay rate. So if it says growth, then we're going to be adding. If it's decay, we're going to be subtracting. Okay, so growth is adding the rate, decay is subtracting. And they're always going to give you a percentage. So for example, if it's, let's say it was like 23% growth, then you got to convert it to 0.23 for R. You got to move the decimal place to the left.
Okay.
Okay. And then T is the time period. It just depends on what the problem tells you. It could be hours, it could be minutes, it could be weeks, it could be years. Okay. All right. All right, so let's do a scenario here. Let's say we have a collector's item. Is worth $5,000. Each year, the item increases in value by 5%. When will the item be worth, sorry, increase by 5% per year? When will the item be worth $6,000? Let's make it a little cheaper, $5,500. Okay?
Yeah.
All right, so we're gonna use this formula here. Final amount equals initial 1 plus R raised to the T. Okay, so let's see if we can gather some information here. What's the value of Y?
5,000.
The final amount, though.
Oh, okay. How would I put that in the calculator?
Oh, right now we're not doing the calculator yet. We'll save it for later. Right now we just want to gather some information.
Okay.
So what's the final amount in this scenario?
5,500.
Yeah. Does that make sense why that's the final amount?
Yeah.
Because it
Actually,
ends
that's
up
two
being
that
this
actually
value
like
of the
two.
problem. And then
Huh?
what's the initial amount?
Yeah, 5,500.
What's the initial amount?
5,000.
So we start at 5,000 and we end at 5,500. Increases by a value of 5%. So that's R. What's R equal to?
5%.
How do we convert that though? If it's 5%, we got to get it to a decimal. What would that look like as a decimal?
0.05 or
Yeah. And it says increases, so we know we're going to be adding. We're not going to be subtracting. So this is going to stay as a plus. If it's decreasing in value, then we got to make this a minus 0.05. Does that make sense?
yeah.
Okay. So I think we have everything that we need. We're trying to figure out when will the item be worth 55. So we're looking for a time. We're trying to figure out how many years will pass. It says when, right? So when isn't, so that's our t. So that's our unknown. That's the what we're looking for. Okay. All right. So now we're going to enter this. No calculator yet. We got to do some work here before we do the calculator. We're going to enter all these values into the equation. Okay. So tell me what the equation looks like.
Okay, it would be 5,500 equals 5,000 parentheses 1 plus 0.05 and then close parentheses. Is that right?
Uh-huh. Is there something missing here?
Oh, the t.
The t. Okay. So we're trying to solve for t here, which is kind of strange, right? Normally, if you're trying to solve for a variable, you can just divide and multiply or add. But here, this exponent kind of makes it a little bit messier to work with. Okay, so we have a special way of dealing with it. But right now, we're just going to try to clean this up. All right, so the way we're going to clean this up, we're going to try to combine things that we can first. I'm going to add those together. And if I do 1 plus 0.05, that's just 1.05. Okay, good so far?
Yeah, I got you.
All right, we want to solve for t, but that t is stuck to the 1.05. Now, normally, sometimes what they would want to do is they want to multiply these together. But the problem is that order of operation tells us exponent takes precedence. So that means we can't multiply until this is completed. And this is not going to resolve itself because that t is not going to go away. So this 5,000 and 1.05 cannot combine together. So remember, our goal is to try to get t by itself. So piece by piece, we're going to try to move things away from the t. So the easiest thing that I can move over is that, or to get rid of, is that 5,000. I'm going to divide the 5,000 over to the left side because remember, our goal is to get t by itself. But first thing, I just want to maybe get this parentheses by itself. And I can worry about the t later. But right now, I just want to move some unnecessary things to the other side of the equation because ultimately we want that t to be by itself. So one thing at a time, that 5,000 is going to go over. Divide. So we see this goes away nicely. All right, what's 5,500 divided by 5,000? You have a calculator?
Yeah, I got it. Okay, it's gonna be 1.1.
Okay, so we have 1.1. The left side cleans up here. Okay. Now we have a special method of dealing with that exponent variable. So basically what we want to do is we want this exponent to come down. If it comes down, it's a lot easier to work with. Then we can divide, multiply, whatever. But that exponent makes it difficult. So what we're going to do is we're going to introduce logs into the problem. And what logs does for us, logarithms does for us, it allows exponents to freely come down because we have a special property available. So we're going to introduce logarithms into the problem. So anything we do to one side, as long as we keep it balanced, we can do it to the other side. So I'm going to do this. I'm going to say log of 1.1 is equal to log of 1.05 raised to the t. Okay. Good so far?
Yeah.
Now, here's what's nice about logs. Once we're inside a log function, that exponent can move without us changing. We can't usually do this. We can't just bring the exponent down. If we do that without logs, then we're changing the problem. But the nice thing with logs is once we're inside a log function, that exponent can come down in front, and it's not going to change anything. But it will make it easier for us to work with the variable. So we're going to just move that t from the exponent position down to the same level as all these functions, as all these terms. Now, remember, this is not log times 1.1. This is not log times 1.05. This is log of 1.1 and log of 1.05. These are values inside the log function. Okay, so we can't, log is not a standalone thing. Like this is kind of within each other. So this is one package deal. That's one package deal. But you see how that t is now easier to work with? So now we're going to simply divide this log 1.05 to the other side, and we can get that t by itself. You see how this goes away here?
Yeah.
All right. Do you have log button on your calculator?
Let me see. I have to rotate it, right?
Mm-hmm.
All right, I got it.
So let's see. Yeah, it's going to be a log base 10. So I think you're going to have to hit 1.1 first and then hit that log button.
Okay, you said hit 1 first.
Yeah, do 1.1 first and then hit the log button on it, and that will.
Okay, I got 0.041.
Okay. Let me just do it for video purposes in case students watching need this as well. So gonna hit that 1.1 like you did. And then there's that log 10 button, which is the same thing as log. Oops. You got 0.041. Jakia, did you get this?
Oh, yeah.
Okay. Okay, we'll do the same thing for the value below, 1.05, and involve log for it. And now we can divide these two together.
Okay, I got 0.196.
Hold on, sorry. Okay, let me see. Oh, you got 1.96, right?
Uh-huh.
So that means because the item is going up by 5% each year, right around 2 years, maybe a little bit under 2 years, this item is going to grow to be worth $5,500.
Okay.
So that's how we handle it. So let me ask you this: what if this was the price of a car? So we know that a car, unless it's a collector's item, a normal car is going to depreciate. So let's say the car decreases by 5% each year.
It would be a
And
decay.
we want to figure out how long it takes before it goes down to $1,000. How would you change how you plug this in?
Okay, you would subtract.
So instead of 5,500, this will be what?
5,000. Well, no, 1,000.
1,000. Okay. This stays the same.
Then, yeah.
And then 1
minus.
Good. 0.05. Yeah. And so you'll get something a little bit smaller than 1. It'll be 0.95, but you do the same thing. You divide over, introduce logs, bring the exponent down, divide over, use your calculator, and you should get something that you can interpret in terms of how long it will take for the value to get from one to the other. Okay.
All right. Yeah, that's one.
So let me see. I think you can apply that for all the problems that. Yeah, you should be able to use this equation. Now for the first problem, it's even easier. You don't even have to do any of this. They tell you what this number is. They tell you this whole thing is 3. So just replace all this with 3. So it'll just be final amount, initial amount, 3 raised to the t. Because they tell you what this value is, so you don't have to even mess with it for number 1. But for number 2 and 3, you're going to have to either add or subtract the rate depending on what the problem tells you.
Okay.
Okay. Give me a second.